Lab 3. So the purpose of this lab was to familiarize ourselves with the basic principles of magnetism, measure and compare distance dependence of a magnetic field due to a small magnet on and off axis, using the Biot-Savart law, as seen above, and the on-axis equation as seen below. So as an overview, we downloaded a Tesla meter app on our phone and aligned our phone with the north and south axis. In Atlanta, the net would be 49 microteslas, and we tried to make that value as close as possible. And then we aligned one magnet and a ruler along the east-west axis. Then we tried to find the maximum x value, the maximum component of the x, and the minimum of y. We marked that off with tape, and then we found the maximum y component with the minimum x component for the magnetic fields. Then we were instructed to collect data at various magnetic fields in the x component and see their distances and see how their distances change. For off axis, we tried to put the phone in the x direction where there was a net magnetic field of 100 microteslas, and then we brought the phone up in the same distance as was in the x direction in the y direction and collected the magnetic fields in each component to get the off-axis magnetic field. Here is our Excel spreadsheet with all our data points and the graph created from those data points. We also had to concern ourselves with the magnetic field of Earth in our net magnetic field for the off-axis field. We did see in the distance dependence part for the x component of the magnetic field that being closer to the magnet resulted in a higher magnetic field, while being further away resulted in a lower magnetic field. So then we determined n and mu using b bar equals constants r to the n, where n has to be a negative value. And from the equation in our graph, which is y equals mx plus b, we could also set up our magnetic field equation to also be in the same form. And by doing so, we found that the slope equals n, so negative 3.2958 equals our n value. Then we tried to find mu using k, which was our ln k, which was our b value. So in order to get k, we had to do e to the power of the b value. Then we set up the b value equal to the constants divided by the constant variables that we knew to get mu. In our code, we used that experimental mu, and we tried to find the b value of a magnet on axis and perpendicular. And we also found it at a 45-degree angle to later compare with our other 45-degree angle values. And here is the finished code. So to compare, the experimental B net was 5.55 e to the negative 5 teslas, while B perpendicular in the code resulted in a magnitude of 14.8 teslas, resulting in a percent difference of 199.9%. These sources of error could be due to us collecting data in a lab that had many electronics. For example, there were wires in the tables, and our laptops, also being electronic, produced magnetic fields. So what if? If we hadn't orientated our experiment to be in line with magnetic north, then the x component would not be as close to zero as possible. And there would be external magnetic fields in the x component, resulting in the magnitude of the x component being larger and not getting an accurate reading. If we had two magnets together end to end, then the magnetic field would increase